You're on.
Hi. Hello everyone. My name is Usman. Today we are going to cover this paper, Neural Relation Inference for Interacting Systems, with Thomas Kiff and Ethan Fateh. They have equal contributions. I just wanted to mention that. Uh, so first of all, I just briefly want to go what the paper is about. So the paper is generally what it does is that it uses variational autoencoder and GNNs to infer the relations between nodes or whatever components or systems you have. So like in my case, when I saw this paper, I thought it might be useful to find the relation between the IC components of the fMRI data we have, or even if not the IC component, then just the fMRI data, uh, and finding the relation between different regions of the brain. So that's why this paper got my attention. So this is the basic idea of the paper, and I've created an outline which I will briefly tell what, like briefly go through VA and GN, and not in detail, just maybe the definition, because we have already covered these two in detail. So then a bit of paper motivation, and then most of the time would be spent on the methods and the architecture of the paper, and then finally few results from the paper. And in the last, like, does it work? Like, it works obviously for the paper, the data set they have chosen, that's why it got published. But would it work in our case? So we will see that. So uh, starting on with VAE. So since we have discussed it multiple times, this just a brief overview of VAs. So you have your input data, and instead of learning just the embeddings of the data or some uh, low dimensional feature vector for the data, we learn the parameters which gives the distribution of our data set. So mostly in most of the literature, the distribution is considered as normal, but in the notes of the slides, I've given some links where it is not assumed as normal, and you can assume any distribution and see how it works. And then you sample from your distribution, you get Z, and then from Z you have your probabilistic decoder to get your reconstructed input. Then in the loss, you have two terms. One is the reconstruction loss, which is this term, the log of P of X given Z. And then you have your KL divergence. So over here, the KL divergence is written in the form of expectation. So that's why you don't see KL and stuff like so. This is just the open form of KL divergence in terms of expectation. So this is to make your distribution closer to the assumed distribution, which is normal in most cases. And this is that your final output is close to the initial input you had. So moving on, GNNs. GNNs, basically you have a structure where you have different nodes and you have messages between the nodes. So the messages are most of the cases the feature vectors of your nodes, and nodes could be anything. Like in my data set, I choose each component of IC as a node, and then the time series is the feature vector of that node. And then you have the links between the nodes, and you can have different kinds of edges. And over here in this image, you can see there are two types of edges, edge one type and edge two type. So in the paper we're discussing the for most different data sets, they assume different number of edge types. Mostly they assume there are two types of edges where one means there's no edge. So because they want to make a sparse graph, so they assign one node to be one edge type to be a non-edge. And then once you have your structure, there are basically two things in GNNs. One thing is how you add the messages from your neighbor, which is this function FT. And then once you have added or aggregated the messages, how you incorporate it with the current embeddings of the node, which is receiving the messages. That is your function Q. And there are many variations of these two functions. So if you come up with your own and it works, you can publish a paper, and there would be high chance of accepting, because GNNs are on the rise and everyone is doing a paper on it. So a very simple example of this FT is this: you add is summation, but you can also have mean, you can have max, but it should be probabilistic invariant, because it should not depend on the order of your nodes, because there are literally many ways to represent same graph in different ordering. So uh, that is GNNs. Are there any questions so far?
Usman, I had a question. I haven't written it
Mhm.
down in the chat, but
Mhm.
on the last slide, I just didn't understand that mathematical notation in the subscript of the sigma. Like, what's K? Like, I haven't
K
seen
is
that.
the, sorry, yeah, I missed that. K is the different edge types. Over here we have two. So
Oh,
if you
okay.
have more than two, or if you just have one, then you can ignore K. Or if you have more than one, then for each edge type, you would do the summation separately.
Okay, thank you.
Yeah, you're welcome. Okay, so what is the motivation of this paper and of my talk? Like, first of all, we know that GNN has worked in many fields: drug discovery, interactive systems, classifying nodes or graphs, in many cases. So, but the problem is that sometimes we don't have the underlying relations between the objects. Like, again, in fMRI, you have the nodes or the regions, you have brain regions, but you don't have, you can find out using some methods the relation between the regions or components, but the ground truth is not available. So this paper is one of those methods which you can apply to infer those relations. And so the question is that, can GNN help us infer the relations? And furthermore, if it can help to get the relation, then would the relations help us when we are doing the any other downstream task, for example, classification or anything like that? So uh, let's see the architecture of this paper. So what I'm going to do is that I'm going to present, since it is variational autoencoder, and the only difference is that what you are learning, and from what you have learned, what you are doing, creating the output. So I'm going to go through in parallel with VAs. So if you know VAs already, it would be very easy for you, which I'm assuming that most of you do, since we have discussed it multiple times. So I'm just going to go in hand to hand with VAs. So similar to VAs, there are three parts. You have your encoder, then you do the sampling, and then you have the decoder. So in encoder, instead of learning the mu, like when we assume it's normal distribution, we learn the mu and sigma. So over here, we learn h of ig, where hij represents the embedding of nodes between node I, embedding of edge between node and I and j. So you have two nodes, I and j, and uh, there's an edge between the nodes. So you learn the embeddings of the edge between those two nodes, and that is represented by h of ij. So that is your encoder. So once you have that h of ij, so instead of mu, you have hij, and then you do the sampling same as VAEs, but over here, your sample variable z, it is not normally distributed, so we won't use the normal distribution. It is uh, discrete distribution, because z over here is representing the edge type between the nodes. So your edge type could be one or two or three, depending on how many edge types you're assuming there are in your systems. So if you have two edge types, then z would be hij would be a feature vector of 2 dimensions, and then z would be sampled from your h of ij. So sample latent variable z from H, same as VAE, but z is discrete, not normal, and it represents the edge type between the two nodes. So a bit of mathematical formulation of that is z of ij is categorical distribution, which is acquired by the softmax of H of ij. So again, if there are two, you're assuming there are two types of edges in your system. So there can be two types of edges between each node, each pair of nodes. So you do the softmax of H of ij. Again, H of ij would be a vector of size 2. And then you do the categorical distribution to get the final z of ij. So once you have that, once you have your z, so now z is representing, you can think of it as z is representing the latent graph. You have the graph structure you have, and then you use z to predict x of tn plus 1 given xt and z. So in terms of VAE again, so in VAE what we do is that you get p of x given z, but over here what they do in the paper is that they predict x of t plus 1 given xt and z. So what they do is that for each time point they take the original input data, which is xt, and they predict xt plus 1 or xt plus 2 or 3 using the z that which is just learned. So that is the overall architecture of the paper. So now I'm going to go through each part in more detail, how
Okay,
each of them is
Usman,
done. Yeah,
sorry to interrupt.
that's okay.
Sergey has a question. Sergey, do you
Hmm?
want to talk?
Yeah, so when you have the categorical distribution, how do they differentiate through it? You still have to differentiate through it, and now you like Z already requires to use the trick, the
Reparameterization thing. Yeah, we'll
yeah,
see
but
that, how they do that. They use Gumbel distribution. They add Gumbel distribution to make the discrete distribution into a soft distribution. And that's how they do. So yeah, they do also have the reparameterization trick, but
yeah, it
we'll see.
feels like the comment is valuable at this slide, but that's fine. Yeah, thanks.
Yeah, actually I had planned to share that over here, but we'll see it in more detail after in at the sampling stage. Okay, moving on to the encoder. So encoder is basically what they do is that they have a lot of MLPs in the system. So they just go through multiple stages of MLP to encode and then also to decode. Uh, Okay, so you have your X, which is the input, and then from X, initially they assume that it's a fully connected graph, so every node is connected to every other node, and then from there, from the vertex region, they move on to the edge embeddings, and then once they have the edge embeddings, they move back to the vertex embeddings. And so far, just assume this last part is not there, because if you start thinking that why they have to go to the edge embeddings again, it can get confusing. So I'll just explain the first two parts, why they do that, and then I would explain why the third part is over there. So starting with the equation number 5. So you have your xj, which is the input. Uh, F of embedding is just an MLP they do to get the embedding H of j. So from H of j, which is the embeddings of each node, what they do is they go to the H dimensions by just taking two nodes, H of I and H of j, and passing it through an MLP, and then you get the embeddings of the edge between the two nodes. And once you have that, using the newly acquired the edge embeddings, they go back to the node level by summing up. So again, like I mentioned, this function over here, they are using sum, which I mentioned in the GNN part. You can use sum, mean, or max, whatever you like. And then so using the newly created edge embeddings, they go back to the node level. So right now at till this equation number 7, So the only thing which was dependent on were xi and xj, because the only thing which was taken as input over here is age of ij, which is created using xi and xj. So each node has only acquired information from its immediate neighbor. So this would be enough. This can also be enough in many graph networks. This is the most they do. Like uh, they only go one hop down, so they only get from the information from the immediate neighbors. But in this paper, what they're doing is that they acquire the edge embeddings again using this HJ2. And the purpose of that is that since it's a fully connected graph, so if you do one hop, you will get the embeddings from your neighbors, immediate neighbors. And but if you do two hops, what would happen is that uh, you would get the embeddings from your direct neighbors plus your indirect neighbors, which are two hops down. So eventually what happens is that each node gets information from the whole graph and not just the neighbors. So that's why this final terms is also there to get information through the whole graph and not just the two connected neighbors. So that's the purpose of this, going back to the edge embeddings in the last term. So this is what you get from the encoder. So h of ij's. So like I mentioned, instead of mu, you are learning this. And once you have that, so any questions before I move on to the sampling part?
Yeah, Eloy had a question. Eloy, do you want to ask him? I think it was on the previous slide.
Yeah, it's about the use x of t to predict x of t plus one plus n.
Yeah.
I was kind of wondering, um, like in terms of implementation, if you would use weights for all of the sort of entries in the
Yeah, I think
xt
I get
input,
you.
that would take a
I
lot
get
of.
your question. So yeah, to learn the encoder gets everything. So for example, you have n time points. So you pass all that n time points to the encoder to learn this age of ij. And then after that, in the decoder part, what you do is that you give xi and predict x1, and you predict x2, and then you give x2 and predict x3.
But are there weights between x2 to predict xt plus 1 or not?
So
As in, it
they
would take a
assume
lot of
that,
weights. For example, let's say our input is a 3D volume of the brain of, let's say, 60 by 60 by 60.
Mhm.
If you have to predict the volume of the brain at xt plus n, and you do that using x of t, that means you would need to do weights for every, voxel in that image, and that would quickly add up to a lot of voxels, right? To a lot of
uh,
weights.
what they do is that they assume that the connections are static. So you just learn one set of connections using the whole embeddings from 1 to n, and then you have the connection between each node, and you use the same connection throughout the decoder part. So it's not that for each t you would have different connections.
Okay, thank you.
Okay. Any other question? Okay. So moving on to the sampling. So what they do is that they sample from h of ij, but they add the g part, g over here, and g is the Gumbel distribution. They add noise to move this hard distribution to like a soft distribution, and they control it with this parameter tau, which is temperature. So if the temperature is close to zero, then you would get a hard distribution of 0 and 1. So it would say if it is equal to 0, exactly equal to 0, so then Zij would be 0 or 1 depending on the edge type. And if it is like not 0, somewhere between 0.5, then it would be a soft distribution between the number of uh, edge types you have. And you can
Oh, hey,
see, yeah.
Usman, Sergey had a question.
Yeah.
Sergey, do you want to ask?
Yeah, well, it's about the previous one. Like, I just wonder if you understand or if they explain clearly why they, maybe I just didn't listen carefully. Why do they go through this series of transformation, node to edge, edge back to node, and then again to edge, instead of just once?
Because once initially you only have your nodes, right? You have the features of your nodes. You need to get the embeddings between the embeddings of the edge type between the nodes. So that's why they go from V to E. That's the first step.
Well, that's the first step. So you're done,
Yeah.
right?
Yeah, but the thing is that you only get it from xi and xj, and you do that only once. So what they do is that they do it twice to get not only from the immediate neighbors, the direct neighbors, but they also want to see how, for example, you have your three nodes, I, j, and k. So if you just do it once, k would be affected by j, but if you do it twice, then you will see how I affects J, and then how that affects translate to
Oh,
K.
this is diffusion process. Every
Mhm.
time they do it, they can go in E to V. They can go few times.
Yeah, so what they're doing is you can think of it as they are doing two hops instead of just one. They can do one. In many GNNs, they only do one, but they want to do it twice. And the reason they mention in the paper is that uh, if you just do it once, so over here, which the terms in equation number 6, so h of ij is only dependent of h on I and h of j, which is just xi and xj. So the embeddings between two nodes are just dependent on the two nodes itself. But what they want to do is that the embeddings between two nodes are not only dependent on the two nodes, but how the whole graph interacts. So that's why they do it two steps, because since everything is connected to everything, so in two steps you can see how other nodes affects I and J, and how that effect translates into
but
their interaction.
but in equation 7, then each node depends on each node. Right? The sum is over everyone, right? Because you don't know the graph yet. So
Yeah, so
everyone is your
initially,
neighbor.
so it's fully connected.
Okay, so you could do it again to sort of like loop twice around the graph somehow, right?
Yeah, so like I mentioned, there are many papers on GNN. This is their method. There are many other papers which do it differently. They do it only once, or they do it even 6 times. I've seen papers they do 6 hops. It's just a parameter that it doesn't. They tried 1 hop or 2 hop, it didn't work. With 6 hops, it started working. So they chose 6 hops for their network.
Okay, thanks.
Mhm. Okay, so in the decoder, so what they do is that now you have your Q of Z given X, and the other input is X of T. So you give both the inputs to your decoder, and you predict X T plus 1. So again, the way they do is that again from Xi and Xj, they go to the H level, which is H of Ij for that T. And then from the H, again, they do the summation, pass it through MLP at the current feature vector, which is X T. And then you get your mu of T plus 1. So this is only done once and not twice as in encoder. So the important thing to some few important things to mention over here is that first of all, you have in equation number 10, you can see it's Fe of K. So depending on how many edge types you have, now K over here is representing the number of edge types. So for each edge type, they use a different MLP, and in their results for different data sets, they are using different number of edge types. And over here, what you can do is that if you want to make a sparse graph, so you can assume there are two types of edges, where one edge type represents there is no edge. So what would happen is that in that case, for example, there are two edge types, k goes from 0 to 1. So they would only do this process the equation number 10 and following 11 and 12 only for one of the H type and not for the other H type, because they're assuming that the other H types mean there is no H. So that's how they would make a sparse graph. So equation number 12 is similar to VAEs. Once you have the output of decoder, I saw many explanations of VAE, and what they do is that they just assume that equation number 11 is the output. So they assume that equation number 11 is the reconstructed image, but actually that is not the case. Even in VAEs, equation number 11, the output of decoder, gives you the parameters of your distribution, which is then used to create your your final output, the reconstructed image. So, but mostly since we deal with images, like many of the examples are for MNIST dataset, so the output is already in from 0 to 1, in the range of 0 to 1, and so is your image. So they just use the output of 11 and assume that is the reconstructed image. And in the code of this paper, they also do that, but in the equations, that is not the case. Equation number 11, the output of decoder gives you the parameters of the distribution, and then those parameters are used to create the reconstructed image, in that case, the future prediction. So that over here is also considered as the distribution is normal distribution. So you learn this mu of j for time t plus 1, and the variance is used as a fixed variance in the code and the paper as well. So finally, the loss is the top term is the reconstruction loss. Since we are assuming that this variable is the variable of normal distribution, and if you remember, if you go back to the loss function of VAE, this is the log of P of x given C. Since we are assuming this is normal distribution, so the loss function is negative log likelihood of the Gaussian, which is this. And the constant over here is just some constant term multiplied by the variance. So this is the standard NNL Gaussian loss. And since you have your discrete distribution, and what they do is that they assume in the paper where they mention the loss function, they're assuming that it's a uniform prior. So all the edge type has equal probability. So that's why the KL divergence term for discrete distribution with uniform prior becomes just the entropy of your encoder. And if you are assuming that it's not uniform, you have some prior. So what you have, the only thing you have to do is that you have to subtract that prior from this term. So yeah, basically that was.
Oh, hi, Usman.
Yeah.
Sorry to interrupt.
So,
Sergey had a question.
I think Harsh answered it. So you like there. I have another question though.
okay.
And another question is, how do you construct the sequence? Because delta t, delta x t, but where does you input the full sequence? It's back to Eloy's question. But then you need to reconstruct the sequence one by one. What is xt? Is again partial sequence on this slide, on this figure.
Yeah. So what they do is that they use one time point to predict multiple time points in the future. So they would use x1 to predict x2 till x10. Then they will use x11 to predict x12 till x20. Then use x21, xt21, and predict 22 till 30 and so on.
How do? They run this encoder multiple times as a
no, the encoder is run only once. So you give everything to your encoder and you learn Z. Then you use the same Z for each xt and predict the future, because they assume that the connection or inference are static. So throughout your time points from t1 till t20 or tn, whatever your n is, the connections would be the same.
So, okay, so they have the graph, they sampled it from the Gumbel, right? Well, from the categorical. Using that graph, they take the real input, all nodes, just the first point. Use the decoder to produce next 10 points. Then they store it, take the 11th point, and use the decoder again to produce. I understand this all can be done in parallel, but basically they reconstruct in the steps by providing input undersampled, basically decimated.
Yes, and they do that because they mentioned in the paper that if you just predict one in the future, then the next time point may not be the difference between the time points might not that be huge, that the model can just ignore the inferences and can still predict the future. So that's why they predict multiple time points. So let's say assume t plus 10 would be to predict t plus 10 you would need the inferences, but to predict just one in the future you might not even need the inferences.
And the predictions don't overlap, like they don't do any averaging of their predictions. The windows
no,
are
they
stacked.
don't overlap. No.
Okay, thank you.
Okay, so for results, I thought we can just see the paper instead of me showing it over here. So let me just.
Usman, I'm sorry to interrupt again. Ilay had a question too.
So my question was more about, so you take every point before, so you use x of t to predict x of t plus n, but you take all of the sort of time points before t to create z, right? You sort of
not before t, everything.
Everything. Just, so it's an anti-causal system where you have information about the future to predict the future.
You have your information about the future to get the to learn the inferences, but when you are predicting, we can say in a matter, because to learn the inferences you saw that output, or like for example when you're predicting t plus 10, you have seen that t plus 10 when you were learning the inferences.
Right, so Z is kind of like a memory, sort of shared representation or memory of the whole time series that helps you
but in
predict
some
any
of the
point in the future.
But in some of the experiments what they did is that they separated, like in the test cases, in the test data, they chose the time points which were not seen in the training data. So for example, what they did is that, for example, your data has 100 time points. So the training was done only, the subjects were different, and also the training was done on first 80 time points, and then the testing was done on the last 20 time points.
Right, but during inference for the testing, you would still give it all of those 50 time points that you haven't shown in the training set.
Yeah. Okay, so let me go to the paper and we can see some results. Just 1 minute. Okay. Is it zoom in enough? Can you like see?
Yeah, I think it looks good.
Okay. So what they have is they have different simulation experiments. So over here they have, let's start with this one actually. Okay, so this is the springs data where you have 5 different balls and they are attached by springs. So the input you get is for each node, for each ball, you get the position and the velocity. That is the input you get, the model gets. And they are connected, some balls are connected to other balls using via springs. So you can see the prediction and the truths, the ground truths. So the highlighted part, the dark part is the prediction that are made by the model, and the kind of blurred part is the input that it receives. So In the images, we can see that there are some variations, like over here, this blue one, this prediction is going down, but the actual was going up. And same is the case over here. The blue is going up, whereas it's not quite so in the actual truth. And some difference between this purple as well. So in terms of the inferences learned, they compared it with the correlation using LSTM. And since they are using very basic kind of LSTM, just the LSTM, nothing else. And so you see a big difference between LSTM and the NRI. But like my point is the effort they put in for the experiments, if they had put it for LSTM as well, then the results would have been different, because LSTM shouldn't be so bad between there should be such big difference between the LSTM and the NRI. So the NRI sim and NRI learn, the difference is that in the NRI learn, they are learning both encoder and decoder, whereas in NRI sim, they only learn the encoder, and then the decoder is the actual model they use to create the simulations. So and the supervised one is that they train the model using the actual relations between the nodes. So that is supervised model, and these ones were unsupervised. The more interesting results are this
Hey,
one.
hey, Usman. Sorry,
Yeah,
not sure if
exactly.
this is a good time to interrupt. Eloy had a question.
Right. So about the previous result, I was thinking, isn't it kind of unfair to compare it to an LSTM when the encoder for the NRI method can see all of the time points you're going to predict, whereas an LSTM only has sort of a memory of all the previous time points?
Yeah, so to make like they mentioned in the text, that to make it fair, what they do is that they have some experiments that maybe that was something about something else. I may need to read it again. No, yeah, yeah, I think you're right. That what they mentioned was something else. Okay, so moving on to this result. So over here, what we see is the MSC, the mean square error between the predictions and the actual results, the ground truth. And static over here is just saying that xt plus 1 is equal to xt. So like my point is that even if you just assume that the next time point is the same as the current time point, the loss is not bad. So the difference over here between static and NRI, let's assume this one, the learned one, like there is difference, but even the static is not so bad. But the difference increases when we predict more in the future. So if you go 20 time points in the future, so this stops working. This goes even worse than this one. So so NRI full graph over here is that they don't learn, there's no encoder. So they assume that everything is connected to everything and you just have the decoder part. And this shows us that the learning of the inference is very important, because if you don't learn the inferences, then your MSE is almost as equal to the static version. Whereas if you have learned the inferences, then you see some improvements on that. And then the true graph is the best kind of model possible using the inferences we have, the true inferences which we have in the supervised model. Then they do another experiments. Yeah.
Hi, Usman. Sorry, not sure if this is a good time to interrupt because we don't really have slides anymore.
Mhm.
Sergey had another question, comment, or something he wanted to say.
Yeah.
Yeah, just a comment. If you look at the springs and like all of the sport systems, I've actually played with the springs system simulating myself for causality as well. Like I'm very suspicious of their noiseless situation. It looks like their stiffnesses are so high and masses are large, so everything is kind of moving slow because like every little noise creates a lot of jitter. Like here, it's like very well behaved systems, very smooth movements and things like that. I wonder if they, well, I didn't see that myself, but like if they commented somewhere, maybe in appendix or somewhere about the noise, what happens when there is
No, they
noise
didn't.
at
Yeah,
this.
that's I'm going to cover that in my next slide, that does it even work? And the point is that, yeah, if you see this data, there's no noise, and the input is the way, the position and the speed of each node. So if you know that this is the current position of your ball and this is the speed of your ball at this time, so the only thing you need to find out is how it is connected to any other ball. If you get that, you can predict with 100% accuracy. But for example, think of fMRIs. Even if I tell you, this is the brain region and this is the current value, and assume all the noise there is. So you compare this figure with fMRI, and then you can think how good it would perform on that. Because I took their code to get this result, this accuracy. Even over here they have some issues, like over this blue one and this purple one, and even for this they are using 50,000 samples for training. And if I just did, what I did was, instead of 50,000, I gave it 1,000 and it stopped working entirely. Like uh, it never went above 55% accuracy. So yeah, if you have so much data and there's no noise, it's as your images are as clean as this one, then yeah, it would work. But who has that? We, at least we don't.
Well, but
So
I wonder then about the mean. They're predicting the mean, and if there is noise around the trajectory, then the mean supposedly is like your momentum, some kind of inertia. It should maybe average over the noise. So I wonder how that works.
yeah, and also uh, one other thing that I noted is that they never went above 5 nodes. Like even on all the experiments, the number of nodes or balls they have is only 5. So if you increase the number of balls, for example, I think they have one experiment on where they, so over here they are doing number of steps increasing, but they also had an experiment where they increased the number of systems, or the number of balls you want to call, and they sorry. Yeah, this one. So sorry. So like you can see, it's the same model, same data set, springs, charge, and this whatever Kuramoto. So when you have only 5 objects, you can see the performance. Over here, for example, you see this one, you have 96%. But if you just increase the number of objects, you go to 75, 10%, 10 objects. So there's a drastic decrease in the accuracy. So from, there's like 20% decrease in the accuracy by just increasing the number of objects you have. So yeah, that's what I mentioned, that when I in the start when I had to read this paper, just the abstract, I had like very high hopes, but yeah, it's okay. It's not that great. So
Usman, I had a question. Sorry.
mhm.
What does the accuracy in terms of percent mean in this case? Like, what does it mean
It's
to have 99.9% accuracy? I'm not sure what the metric is.
so this is the interaction, like you predict these are the interaction between the nodes or whatever, the whatever you want to call the systems, and then you compare it with the actual uh, the actual graph you had, so the actual connections you had in the graph.
Sergey, what's up?
Yeah, well, the interesting part when metric, you know, the whatever the lies, big lies, and metrics, it's very interesting because what are we interested in when we're looking at the graph? We're interested in two questions which are separate, and when you combine everything in one metric, that could be tricky. But we're interested in edge omission and edge commission. Like how many extra edges does your algorithm add when it's not, like when the edges are not there, and how many edges the algorithm misses when the edges are there. And when you show some kind of an abstract accuracy, it's very hard, like, because sometimes you like, those are very different things and they're meaningful. Extra edges versus, okay, I missed the edge when I should have had it. Well, 99.9, probably they kind of putting everything together, but you can hide false positives and false negatives by, you know, counting them together. So just a thought, just like a single metric is not informative in this case, I think.
Thanks, Sergey. Yeah, and thanks, Usman.
Yeah, you're welcome. So yeah, that's it from me. If you have any other questions.
I have a couple of questions actually.
Okay.
So you said, the size of K is 2, right? The size of the edge embedded.
Depends on the experiments. Later on, they have experimented on the foot NPK players, and over there they had also tried with 4 types of edges. But yeah, mostly there were 2.
Okay. And the second one is, when you look at the decoder, they train a decoder on every edge type, right? I couldn't make out how they encompass all those different edge types in the objective function.
So what they do is that they create a separate MLP for each edge type, and then for each edge type, they predict like using the each edge type they had the IJK, so they use a different MLP for that.
This is good. This is good. And yeah, this is a totally different question. Somewhere in the paper they explain that this work implicitly captures the relationships between different components of the system. So can you explain the difference between implicit and explicit? Or the other way around, this is explicit. This captures the relationships explicitly, but other papers in literature capture the relationships implicitly. So what does that mean?
I'm not exactly sure because I think I didn't
go for
pay
it,
that.
Sergey.
Yeah, I think I didn't pay that much attention.
Yeah. I think what they mean is like when you can train a fully connected neural network to predict your next time points. And in order to predict those next time points for a list TM, it should understand who influences who, in a sense, right? But you don't have a way to ask it, what is the actual influence graph? And here they are saying, okay, here's the influence graph explicitly.
Okay.
Yeah, Eloy, I think that's same.
And
so this is like an unmoderated time, right? So people can just talk when they want.
Well, I guess we want to avoid the situation when somebody gets interrupted or somebody is shy and they don't talk, but they want to talk.
Yeah, I have one last comment about this relationship between LSTMs and this one. I think you're talking about, it's kind of cheating because LSTM only has the past information. Okay, look at what's happening in the encoder and decoder. The encoder is only inferring the relationships with no information as to what's happening in the temporal dimension. It's only the decoder that's predicting one time step, into the future. So when you look at just the decoder, it's effectively doing what an LSTM does by virtue of the gated recurrent unit. So I think this is definitely a valid comparison there.
But Z is created using all time points. So there is information.
But there is no
in
temporal
Z.
information that's being captured. It only infers the relationships. That's it. The relationship along the temporal dimension is not captured. And Z is just, whether there is a relationship between them or not, a causal relationship or whatever, but not in the temporal dimension.
Okay, I thought it was also
At least that's my take, actually. But yeah,
Yeah,
No,
they give the
it
whole
would make more
Z,
sense.
but they are not inferring the
they use the entire
temporal.
trajectory. Absolutely, I'm not denying it. But then
Yeah.
that has no bearing on whether there is a causal relationship along the temporal dimension.
Yeah, that is only done
Right,
in
but
the
it's
decoder.
still, my point is, let's say you have a point here and then like a point here. Having seen that in the encoder does help because it can be, I don't know if that makes sense. Like, even if you don't know that this point goes like this, you've still seen this point in the encoder and that information about that location being in the time series that is in the Z.
I don't know how to disentangle that. I mean, there is a point there, but only thing I think of it is Z only tells whether there is a relationship or not, some sort of relationship.
So that I agree with, but it is kind of like saying, okay, let's say, okay, I want to predict where this spring goes, and these points are all points that are, in the time series that is going to come, but we don't know the relationship between these points. That's kind of like saying but it's still kind of, I guess, a little easier, I don't know. It's like,
what is easier, relationship prediction or time series generation?
well, I think if you already know that certain points, like if you could know, let's say that you could know that certain points exist in the time series you're gonna predict, even though you don't know the relationship between those points, it still makes it a little easier than with LSTMs, where even the encoder does not have any knowledge about the previous time steps. I don't know if that makes any sense.
I think he's trying to say that Z implicitly embeds the information, the temporal information, basically.
No, not temporal information, but if you know, for example, for a spring that it's going to be at this location, because that's not temporal information, that's just spatial information. That means that spatial information about the future time point is in Z. You don't know when it's happening or what the temporal relationship is between the other spatial points, but there's still some extra knowledge that
That's
you
what I
have
said.
over
Z
LSTM.
has that information of where it's going to be in the future. That's exactly
Exactly
what I said. That's how you're characterizing it.
Yeah, so that's why I think it's unfair, because LSTMs do not have any information even about spatial points in the future. They have no extra knowledge.
I didn't really read how they do the experiment, so I really don't have an
But
answer.
when they are doing LSTM, they do they do correlation LSTM. So they use the correlation using the data, and then they use the LSTM. So I think the only difference is that instead of learning the relations using their method, they use the correlation and they find the covariance matrices between the points, and then instead of their decoder, they have the LSTM.
But yeah, this is good. Thank you so much for your time. That was definitely good. I enjoyed this talk, definitely.
Yeah, thank you, everyone. So we don't have just a quick announcement. Yarong kind of just couldn't last moment, basically couldn't make the talk, so we don't have a talk for next Friday. Let's continue in the channel and decide what paper we're going to discuss for next Friday.
I think William wanted to discuss neural Turing machines.
I don't know, William, what do you think? Are you ready, or will you be?
I mean, I'm 1 week is risking it, but it's possible. But I don't want to commit to that. I'm in the middle of moving. No, I'm not going to be ready in a week.
I can sort of chat, but I will not have like a fully fleshed presentation about the neural tangent kernels and about Pedro Dominguez, the path kernel paper. It will be more of like an open floor discussion rather than I will explain you how it works, but I can point to some interesting observations that he is making there. How about that? Yeah, we could like if we don't have anything else, but we only have 2 talks after that planned, so we need more. And let's go back when you have time to our Google Doc. We have a lot of unallocated papers there that we all thought it would be good to read, but we didn't put them on the schedule. No one took ownership of them. Please take a look at that list, either add your paper or pick one paper from there. But otherwise, yeah. Thank you so much.